Hi, everyone, and welcome back to Psych 3510. In this module, we actually in the course, are taking a shift away from the textbook material and the inquisitives, and we're going to be entering the world of statistics. So we're going to be doing things slightly differently for the next, I think, two or three, 2.5 modules. Um, we won't be doing any of the inquisitive quizzes through the publisher website. Instead, we'll have quizzes over the lecture material or the outside readings that I'm going to be bringing in. And then our workshops are mostly going to be things like practice problems, maybe doing some practice problems, taking a picture of them, uploading it, that sort of thing. I'm going to be sending you an email and posting an announcement that details all of sort of the shifts and changes that are going to take place. But the major thing to keep in mind is that we are still going to have a quiz over every topic. It just won't be in inquisitive. And we are still going to have workshop credit for every topic. So you still have 3 quizzes and 3 workshops per module. That doesn't change. The nature of what that looks like will change, but I'll be sending you updates about that, so don't worry. So what we want to do today is introduce the world of data, specifically data visualization. We're going to start with some things called frequency tables and frequency distributions. So I want you to imagine that we've taken all of that information from the last few modules. We learned, how to sample participants. We learned how to build an ethical study. We learned how to construct good surveys and valid and reliable surveys. We learned about our validities and our claims. And we actually went out and did the thing, right? We actually went out and collected some data. What do we do now, right? What's next? So after you actually have some data, the first step is that you want to get sort of a rough idea about what those data are telling you or showing you. Oh, I just realized I'm in presenter mode. Sorry about that. You want to get a rough idea about what those data are telling you. Basically, you want to describe the data. And this brings us to a distinction in the world of statistics between descriptive statistics, those that help us describe or summarize a set of data, and then the world of inferential statistics, which allows us to draw conclusions from our data, make inferences about our data. So the ultimate goal is to get to inferential statistics. That's the good stuff. That's what we want. That's the meat and potatoes. That is the act of science, right? Which is collecting data and then drawing a conclusion and making an inference to the world from that data. But we're going to start in the world of descriptive statistics. You already know some descriptive statistics, things like mean, median, mode, range. But there are going to be some other things that we involve in descriptive statistics that you're probably not as familiar with. So remember, our distinction here is descriptive statistics help us get an idea, a rough idea about what the data say or what the data look like. We describe the data. Whereas inferential statistics draw conclusions about the world from our data. We're not going to do that yet, but we will later in the semester. Okay, so our research question was, how difficult do you think this class is? We collected data from a number of students, and we gave them a 7-point Likert scale that anchors from very easy to very difficult, right? So if they answered a 1, they think the class is very easy. If they answered a 7, they think the class is very difficult. And so here we have our data set. Here we have a matrix of data, right, responses to our question, such that each number represents the response of a single individual, right, a single student or participant. Now, it's difficult to conceptualize anything about these data if we're just looking at like a spreadsheet of numbers, right? It's too confusing. The information isn't organized in such a way where we can describe it adequately. So our first step is going to be to organize the data. One way we can do that is through what's known as a frequency distribution table. So this is really simple. The first thing we do is list all the possible scores from our data collection instrument from high to low. So this is any number that someone could possibly have scored. In our question, we gave them a 1 to 7 scale, right? So the possible scores were 1, 2, 3, 4, 5, 6, or 7, right? So we list those numbers from high to low, even if no one responded with that score, right? Even if there wasn't actually, let's say, someone who said a 4, right? Because if no one said a 4, that's still valuable information, right? The absence of a 4 is an important point for us to consider. So you list all possible scores, even if no one actually responded with that score. So that's step one. So we list all possible scores from the highest to the lowest, even if no one obtained that score. Really important here to list them from high to low. That's going to be important for some things we do later. You do not want it to be low to high. Step number 2 is to fill out the frequency column. So this is noted by an italics F or an italicized F that stands for frequency. Again, a really simple operation here. We basically go and count up how many people scored a 7. How frequent was a 7? Well, if we go back and we look at the data, there was only 1 7, right? Search the data, 1 7. So we put a 1 under frequency. That tells us that one participant scored a 7. Now we want to know how many people scored a 6. So we go back and look at the data. 1, 2, 3, 4, 5 6s. So we put a 5 under our frequency column in the 6 row. This tells us 5 participants responded or scored a 6 on our measure. We had 5 5s. 1, 2, 3, 4, 5 5s. So we put a 5 there. So on and so forth, etc. for all of our scores. We had 1 4, 3 3s, 2 2s, and 1 1. Again, remember, it's okay if no one has that score. You would just put a 0, right? Because there's 0 occurrences of that score. The frequency of that score is 0. That's still an important point. Okay. So we haven't done anything complicated at this point. We have listed the possible scores from high to low, and we have counted up the frequency of occurrence of each of those scores. Even with this small amount of work, we already have a data organization system that allows us to start describing the data. The first thing we can do to describe the data is we can determine how much data we have, how many participants are in our data set. That's simply the sum of our frequencies, right? Because if this 1 represents 1 person and this 5 represents 5 people, then if I add these numbers up, it tells me how many people I have in the data set. So the sum of F equals N. N is a special symbol we use in data science to represent the number of participants in a data set. So N represents the number of participants. So we can do some other things too that we'll get to in a second. So we want to know the number of participants. We just add up all of our Fs, and boom, we have 18 participants. Easy enough. So That's the first thing we can do to describe our data. The next thing we can do, for example, is determine the maximum score. What is the highest score that someone achieved? Not that was possible, right? This tells us which scores were possible, but what's the highest score that someone actually achieved? Sorry, my PowerPoint logic is a little annoying here. So, our maximum score was a 7, right? Because we have one person who scored a 7. That's as high as you can get, right? That's the maximum score. We can move on to the minimum score. The minimum score was a 1 because we had one person who responded with a 1. We could do something like range. Sorry about this. This is super annoying. We have the range. So range is just right the highest score minus the lowest score. So our range in this data set is 6 because someone scored a 7 and someone scored a 1. So 7 minus 1 gives us a range of 6. So those are very discrete, maybe obvious things that we can do to describe the data. But we can even go a step further and we can start doing some, I don't know, maybe what you would call conceptual descriptions of the data, such as where do the scores cluster? So if we look, oh man, this is really screwed up. Sorry about that. That F should obviously be over here. If we look at where our scores cluster, like where do people group together? They group together around 5 and 6, right? We have 18 participants. Remember, 18 was our sum of F. 10 of them, so over 50% of the data lie in the scores of 5 and 6. So if we can think about what that means, right? Our measure here was how difficult is the class, 1 being very easy, 7 being very difficult. So we can already say something about the data that's quite descriptive. Most people find the class pretty difficult, right? 5 and a 6 is above average difficulty. It's not a 7, right? It's not the hardest class I've ever taken, but most people find the class fairly difficult, right? We can make that description based upon where the scores cluster. And of course, we could look at the sort of larger spread of scores as well. So let's take this new data set and discuss our spread of scores as well as where they cluster. Right? So notice I switched up the data here. Let's imagine that instead of what we had previously, this is what our data looked like now. Where do the scores cluster? They cluster at the bottom this time, right? We have all of these scores, all of these people giving 1s and 2s. So most of our students find this course to be quite easy, maybe very easy. And notice that we have no scores at the top here. So no one finds this class particularly difficult. The class is either sort of moderate, right, average, or very easy. Notice that our range, right, the spread of our scores is constrained here because we don't have scores, we don't have people responding across the full spread of scores. The highest score here is a 5. So what this means is that people are more uniform in their evaluation of the course. This tells us that on average, the scores are clustering closer together. Their spread is less, right? There's less spread. There's less variability in this data when compared to the other data, right? Notice that there's more spread here. There are responses across the entire possible breadth of scores. So, even with this very simple operation, like listing the possible scores, counting up the ones that occur and their frequency, we can do quite a bit of description. It's simple description, but it's nonetheless description. It tells us something pretty valuable about the data, and we haven't really done much, right? We've done basically no math beyond addition. Obviously, we're not going to leave it there. We're going to get a little more complicated. And so the next step is called relative frequency. So we're getting new data. We swapped out our old data for some new data. Imagine this time we have some question where our possible scores are 6 to 1, right? That's what our score column tells us. And we've already done our frequencies. We've gone through and we've counted up all the scores. We had one person respond 6, 0 people got a 5, 2 people got a 4, so on and so forth. 10 people got a 2. And so a question you might want to ask is something like, well, what proportion, what percentage of scores fall into each score category, right? So what percentage of people scored a 6? What percentage of people scored a 3? What percentage of people scored a 2? So on and so forth. That's what we call relative frequency. So relative frequency, you'll see as rel f or rf, is simply the proportion of responses at each score value. So we have one person who scored a 6. Well, what proportion of the data is that one person? We have 2 people that scored a 4. What proportion of the data are those 2 people? So you just do a fraction, right? It's relative frequency equals the frequency of that score over the total number of responses. So here, the first thing we want to do is determine our total number of responses in. So we add all of these up. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 10 is 16. 16 plus 4 is 20. So we have n equals 20 total responses. And so for each score, we're going to take its F value, its frequency, and we're going to divide by big N, by 20. And then we're going to put that resulting proportion into a new column of relative frequency. So a score of 6 occurs one time. So 1 divided by 20, because 20 is our total N, equals 0.05. That means 5%, right? You move the decimal point twice, but we're going to keep it at 0.05 for right now. So a score of 6 occurred one time, and that represents 5% of our data. We move on to the other numbers, right? You can now go on and do this for all of them. A score of 2 happened 10 times. 10 divided by 20 is 0.5, right? 10 is half of 20. So the relative frequency of score 2 is 0.50. It occurs 50% of the time. We can do that for each score, right? Score number 1 occurs 4 times. 4 divided by 20 is 0.2, or 20% of the time. Notice how score 5 has a frequency of 0. No one responded with a 5. That's fine. 0 divided by 20 is 0, right? The relative frequency, the proportion of the score 5 is 0 because it doesn't exist in the data set. So to find the relative frequency, we simply take each F and we divide by the total number of participants, and we put the resulting proportion in the appropriate column. Easy peasy, right? But what this tells us is maybe more of a mathematical way of construing clustering and spread, right? Because now I can make this statement that 70% of people, right? 0.5 plus 0.2, 70% of people scored a 2 or a 1. That's a valuable thing to be able to say. That's a valuable description of our data. And in fact, our next step is going to be to formalize that same idea using cumulative frequency and then, cumulative percentage. So, what we want to do is create a new column called CF for cumulative frequency. Cumulative frequency tells me how many people or how many responses exist at or below a particular score. So the accumulation of scores up until that point. So let's take it step by step. Here, our data range from a score of 17 down to a possible score of 10. Here we can see our frequencies, how many times each of those scores occurred. And here we can see our cumulative frequency, meaning how many scores occurred at or below that particular score. So for example, we take the score of 11. There were 2 instances of 11, and there was 1 instance below 11, giving us a cumulative frequency of 3 for 11. 3 people scored at or below 11. Notice here that the bottom row is super easy because there's no one below it. So the cumulative frequency of 10 is just how many people scored a 10, right? It's 1. So 1 person scored a 10. 3 people scored an 11 or a 10. And for example, 17 people scored a 15, a 14, a 13, a 12, an 11, or a 10, right? So now we jumped up there, but we're jumping to sort of make the point of how this works. So if I want to know the cumulative frequency of the score 15, what I'm asking is how many people scored a 15 plus how many people scored a 14 plus how many people scored a 13 plus a 12 plus an 11 plus how many people scored 10, right? The accumulation of scores up to 15. So 4 people scored a 15. 6 people scored a 14. 4 plus 6 is 10. 4 people scored a 13. 10 plus 4 is 14. 0 people scored a 12. 2 people scored an 11. 14 plus 2 is 16. And 1 person scored a 10. So 16 plus 1 is 17. So we can look at any point in this cumulative frequency column, and the number conveys to us the information that is how many people scored at or below the corresponding score. So 19 people scored at or below a 16. 13 people scored at or below a 14, right? You add up the frequencies and then you put that number over to the right in cumulative frequency. So if you want to know how many people scored at or below a 13, well, 1 person scored a 10 plus 2 people scored an 11 plus 0 people scored a 12 plus 4 people scored a 13. 1 plus 2 plus 0 plus 4 equals 7 is the cumulative frequency for 13. 7 people scored 13 or below. So that's kind of valuable, right? Also, sorry, I forgot to mention, your cumulative frequency at the top should equal your N, right? Your number of participants, because, right, the highest possible score is the ceiling of your responding. So everyone should be included at that point. If you get, it's a nice little check you can do. If you get to the top row, your cumulative frequency should equal the sum of your Fs, right? That makes sense because that's what you're doing. You're starting at the bottom and adding up all of your Fs and then putting that number here. So your cumulative frequency should equal your sum of F, or your N, your number of participants. Now, The next step to make this really valuable is called a cumulative percentage. A cumulative percentage is going to tell us the percent of respondents at or below each score. So, for example, if I wanted to say what percentage of people score at or below a 14, I know the number of people who score at or below a 14, but I don't know the percentage of people who score at or below a 14. So, to do that, I mean, it's just a simple calculation. You take the cumulative frequency of each score, you divide by the total, right? How many scores there are, and then you multiply by 100 to move the decimal the two places you need. So we're going to take each cumulative frequency, divide by n, which in this case was 20, right? I have 20 data points, and then times 100 to move the decimal point. So let's see what that looks like. Let's start at the bottom. I have the score of 10. 10 occurred once. 10 is the bottom score, so it has a cumulative frequency of 1. So I go 1, which is its cumulative frequency, divided by 20, which is the total number of participants in the data set, times 100. I'm going to use this for times instead of x because x is used for other things in algebra. So this little star is going to typically denote multiplication. 1 divided by 20 times 100 equals 5. That tells me that 5% of people scored at or below 10. Of course, there is no score below 10, so this just tells me that 5% of people scored a 10. Let's move on to the next one. 11. 2 people scored an 11, but there were 3 people at or below 11, right? So its cumulative frequency is 3. So I put that in the numerator, 3, divided by the same number, 20, because that's my number of participants, times 100 equals 15. Now be careful. This doesn't mean that 15% of people scored an 11. This means that 15% of people scored at or below an 11. 15% of people scored at or below an 11. The cumulative percentage up to this point. So we can do it all the way up. The cumulative percentage for 12 is also 15%. Why? Well, because no one scored a 12, right? It has a 0 in the frequency column. It means in this data set, there was no score of 12. So what that means is that our calculation actually stays the same as the score of 11, right? There are still 3 people at or below 12. There was 1 10, 2 11s, 0 12s. So its cumulative frequency is still 3. It's the same as the score 11. 3 divided by 20 times 100 equals 15. Let's do it for score 13. There were 4 scores of 13. It has a cumulative frequency of 7, right? Because there were 4 plus 0 plus 2 plus 1 people at or below a 13. 7 divided by 20 times 100 equals 35. So 35% of our participants scored at or below a 13. We can continue to do this, right? We take our cumulative frequencies, we divide by n, and we multiply by 100. What I want you to do, just as a quick little practice, I want you to finish the table. So press pause, finish the table, and then come back and check your answers. So I'll give you a second to do that. Okay, hope you're back. Let's check our answers for the rest of the table. So we had 85 is the cumulative percentage of 15. That's 17 divided by 20 times 100, right? 17 is the cumulative frequency. 20 is our n times 100. So on and so forth. your cumulative frequency should always end with 100%. Why? Because the highest possible score will contain all of the data either at or below it, right? That's what it means to be the highest possible score. All the data are at or below that score. So 20, right, is the cumulative frequency of the score 17 because there were 20 people at or below 17, right? If we add up our frequency, if we sum our frequencies, it's 20. 20 is also our N, so 20 divided by 20 is 1. 1 times 100 is 100%. So we can now say really interesting things, like 35% of our sample scores at or below 13. That's really helpful. I mean, this is basically what colleges do for admission to college, right? This is how we look at things like SAT scores and the GRE when you're trying to get in grad school, or the MCAT when you're trying to get into med school. When you took the SAT or the ACT and you got your scores, it tells you your score, right? You scored 1,150, but then it also gives you a percentage, right? It tells you were in the 63rd percentile. What does the 63rd percentile means? It means that 63% of respondents scored at or below your score, right? You are in the 63rd percentile. You plus everyone who scored an 1150 plus everyone below you equals 63% of the data. So it gives us a really good metric for how a particular data point falls in the span of our data, right? In the spread of our data. It's going to tell us, are you average, right? Which means you're around the 50th percentile. Are you below average? Maybe you're around the 15th percentile. Are you above average? Are you at the 95th percentile? So this is incredibly valuable. I mean, this is used constantly in the world to evaluate people, to evaluate performance, to make decisions, right? Georgia State might say something like, we want to raise our admission standards, so we only want to let in the top 40% of applicants. And then they could rate applicants, and then they would essentially do this, and then say, okay, at what score, at what point is the top 40%? And then they send those people acceptance letters. Right? This is how college admissions essentially works. This is very, very important in the real world, in the business world. If you work for a large corporation, it's likely that you'll be evaluated like this. This is how people get into med school. If you go into the military, when I was in college, I had some friends who were in ROTC. So they were like in the military while in college. After they completed their degree, right, they transitioned directly to the military. But the whole time that they're in ROTC, they're taking all of these evaluations. They're doing these tests. They're going on these trips, and they're going to different bases and doing all this stuff and earning all these accolades. And all of that over their 4 years adds up and then becomes a score. And then that determines your job in the military when you once you graduate. So this is incredibly important, and is used every day in the real world. Okay, so I'm going to stop us here. This is going to be part 1, because what I want you to do is take these data that you see in front of you on the screen, and I want you to make a frequency table that has a frequency column, a cumulative frequency column, and a cumulative percentage column from the following data. So the following data, we asked teachers to rate high school seniors, where 1 equals a poor student, 10 equals an incredible and amazing student, the best student I've ever had. So press pause, or no, actually, I'm gonna end the video here, and then part 2, we're going to start with going over this practice problem. So take some time, create a frequency column, a cumulative frequency column, and a cumulative percentage column. Go back in this lecture or in these slides and look over those steps, right? This is not a test. You don't have to do it. It's open note, right? Go look at the lectures, look at your notes, do this to the best of your ability, and then start part 2. And we will begin part 2 with going over this practice problem. So thanks, everybody. And I will see you when we go over the problem and finish the lecture. Have a good one.